Where are the office hours?
好像看一个标准一点答案。
On the campus? Are they not Okay. All right, let's start. Okay, so today graph, what is the picture on the right side? So it's
Where
very
you
basic.
currently are in the algorithm.
Yeah, so this is the set of the graph that you get by just the edges that you've chosen so far. Okay. So this picture, you should be very clear what these two pictures are. Okay. And so these are all the edges I have picked so far. Now, how does this relate to the T I have drawn here? The T is some tree that I have come up with, and then I do that, right? So that is now pretty clear. So now what is this?
It's after the algorithm ends, all the things that would have been added, right?
No. Yeah. So what is the T? Yeah.
It's a minimum spanning tree that doesn't contain
It is a minimum. It's not about containing EK or not. It's a minimum spanning tree that contains everything that I have added so far. Okay.
on the left or
On the right. So this tree contains every edge on the right. Okay, I don't know if it's clear from the picture, but it's supposed to be. Okay. So I mean, maybe I think one of these edges has to be way on this side, but yeah. So this tree contains all the edges on the right. And how do I know there exists such a tree? Sorry? So I'm saying at this point of the algorithm, these were all the edges I've added so far, not including EK, right? And I'm saying that there exists a minimum spanning tree that contains all those edges, and that's the tree I've drawn here. Why do I know there exists a tree that contains everything so far? Yeah, it's by the inductive hypothesis. Okay, so this is what we do in induction, right? We assume that the statement we want to prove is true until this point, then we prove it at the next time step. Okay? So the T I have drawn is whatever you get from the inductive hypothesis at this time step. Okay? Then I'm going to prove the same thing for the next time step. So that's the structure of the proof. Okay, so you should always know what the structure of the proof is, and then you can fill in the details. Okay, so that's why it's important to understand this notation. Okay, so T is the tree that was guaranteed by the inductive assumption. Okay, and now I want to go ahead and prove it for the next step. Okay, so that's what I'm doing now. Okay, so this is the T that I've drawn. Okay. And now the argument was what you were saying, which is that if T had already contained EK, then there's nothing to prove because T itself works at the next step. Right? Because I need to, what does it mean to prove the inductive step? Right? So I have to say that if there was a tree that contained all these edges, then there's another tree, potentially a different tree, that contains all the edges that I have chosen until the next step. Okay, because that's the claim that I want to show by induction. And so if this tree itself works, then there's nothing to prove. Okay. Otherwise, I've got to construct a different tree. Okay, and that's what we are trying to do now. Okay, so that's the structure of the proof. So assume there is a tree T. Yeah, maybe I'll write this down. That contains edges chosen until EK minus 1, and then you prove that there's a T prime that contains edges chosen until EK. Okay, the same claim until EK. Okay, so that's what we mean by proving this claim by induction. And if T itself works, then you're good. Otherwise, T doesn't work, which means that EK was not in T. Then I said that in the set of look now at this subgraph. Let me call this one H, so that you guys, we have T and we have H. Okay. H is just it's a graph that contains only the edges that I've picked so far. So now we are saying that look inside H. this ek has to go across different components, otherwise I would never be trying to add ek. So which means that there was some component S of H onto which ek was inserted. Yeah, I could also have considered S to be this one. Okay, but I'm just arbitrarily choosing it to be this. So that's what it is. So this one is S. And now I'm going to do a little bit of back and forth argument between these two graphs. Okay, so one is H and the other is T. Okay, so that's why I wanted to make sure everybody knows what H and T are. So, alright, so now let's look at this edge EK in both these graphs. Okay. So here it's an edge that goes from this component S to something outside S. Right? So now let's look in the tree T. Okay. In the tree T, there is some path that goes from one endpoint of EK to the other endpoint. Right? So how would that look in this S? And it will look something like this. Right? It's some path that went from one endpoint to the other. Is that clear? Okay. So, but what you can guarantee from this is that there is always some edge that crossed the boundary from S to something outside of S. Okay, so the key step is, let me just insert it. The key step is there exists an edge on the path between the endpoints that crosses S. Okay, so is this clear? So this path, you can trace it in the graph page. And in that there is some edge that crosses this boundary. Okay, so in this case, if it's only two vertices, presumably there is an edge that went out like this, out of this EV. Okay. Now, what can you say about this edge? Okay, let's call it E prime. Could it be an edge that you've already considered? And why not?
Because you sorted it in weighted, in order of weights.
Yes, but I mean, it could have come before, but maybe you decided not to add it, right?
Yeah.
Could you have decided not to add it?
No, because it connects things that weren't connected before.
Exactly. Okay. So if this edge had been something you've seen before, then you must have added it. And by definition, this was an edge that we said there was not in the original. Right? So that's why you can assume this edge has a weight that's bigger than or equal to the weight of EK. So what we can say is that the next step is weight of E prime is bigger than or equal to weight of EK. Okay, because if not, you would have seen it before, and in which case you would have added it. And now we are nearly done, right? So now in this tree T, right, I have found a cycle that contains an edge, let's call this one E prime, and this EK. Okay. So let's isolate this cycle. So in this T prime contains this EK and this E prime. Okay. and there's the rest of the tree somewhere out here, right? Yeah, this also edges on. Okay, so E prime is there, Ek is not in the tree, so this is a dotted line. So. And I know that weight of Ek is smaller than or equal to weight of E prime. So now can we show there's a different tree that has a cost that is not higher than this, which also works? Now can I, so remember what is our ultimate goal, right? Our ultimate goal is prove that there exists a T prime that also contains Ek and should contain all the edges so far. So now can you come up with a tree which contains Ek and all the edges considered so far? Yeah?
If we delete the entire path which contains E prime,
Oh, you want to delete this full path?
yeah, and replace it with K.
So the problem with that is that you don't necessarily remain connected. Like just consider this picture, right? So here if I remove the whole path, then I would just have something like this. This is this edge.
Just 1 inch.
Yeah,
Right,
so
that's the one.
what you're saying is, yeah, so just observe that if you deleted the whole path, things don't get connected because you might end up in a situation like this. So what you've got to do is just remove E prime and add Ek. Okay? And just swap this edge with that edge. Okay? Now your tree looks a little odd, it looks like there's that edge, there's this edge and everything, and there's also this extra edge. You can show easily that this tree this is also a connected thing. It connects every vertex in the graph to every other vertex. And this has cost that is at most the cost of t. And the reason for that is just this inequality. Okay, so cost of t prime. So t, actually let's define t prime. T prime is the tree with Ek replacing T prime. Okay, and we know that cost of T prime is less than the cost of T, which means that it's also an optimal span. It can't be strictly less because cost of T was supposed to be the minimum span. Okay, so it has to have the same cost.
Does it matter which one is E prime? It just has to be something that hasn't been added yet.
It has to be something that crosses this cut
Okay.
in edge. So that's important. Yeah, any other? Yeah, so alright, so that's basically the proof. Okay, so you want to, it's by induction and you show that you are correct at every step. Okay, so if you don't fully follow it, just go back and look at it. It's a clean proof and it's kind of a model for a lot of greedy proofs. Okay, so you always say that greedy never takes us off path from optimal. Okay, so this is one powerful way to show that greedy algorithms are correct. So you say that there is a full solution that's a completion of this solution. Yeah, because the point is that greedy solutions never backtrack, they never remove things.
So this is like a general solution for all greedy algorithms?
No, I mean it's not. So similar ways of proving things work for greedy algorithms. So I mean this is like a general proof technique where you show that in some sense there is a full solution that contains everything I've picked so far. That general principle is something that is very often useful in greedy algorithms. So there are some cases in which maybe it's very tough to prove things like this. Prove it this way. Okay, maybe there's a different proof that works, but that's the
Can
way.
you just recap the second slide after this, just like a recap of
Oh, of what happened. Okay. So we want to show this, right? So whatever is happening there is basically an execution of these two. Okay, so this is the thing that we want to prove by induction. Right? There is a tree T contains all the edges so far. Right? And this picture shows two things. One is the tree T that contains all the edges chosen so far, and the right side is a subgraph H, which is literally all the edges chosen so far. Okay, so these are all the edges chosen so far. This is the tree T that contains all of those guys. And we know that T is a minimum spanning tree for the full graph. So now what we are saying is, now let's look at the edge Ek that we want to add. So if this edge is already in T, then there's nothing to prove. T prime equals T works. But if that edge Ek is not in T, then there is a path in T that goes from one endpoint of Ek to the other endpoint. And let's look at this path. Now let's look at this path in this graph H. Okay, so it's the same path. So it goes from one vertex, it goes from one endpoint to the other. Okay, so this is the path that I drew. Now it has to cross the cut. It's going from one component or in H to another component. Can't be in the same component because otherwise you would not be trying to add Ek. So it will be crossing components. Now look at the component that contains one endpoint. Let's call it S. Okay. So this path has some edge that crosses the boundary. Let's call that edge E prime. And E prime is a tree edge. Okay. So and then we are saying now consider a new tree where E prime is removed and Ek is actually added. And this argument shows that basically this is a better tree. So that's
E prime existed before
E prime existed in T.
Ek was there in T, and now you're basically removing E prime and putting Ek.
Yes. So Ek was not in T because all the edges so far have been there. Ek you are considering adding now.
So why do you have to replace E prime and Ek?
Because you now need to produce a tree T prime that contains Ek also.
So you just have to tell why would you want to add Ek. And the reason would be that
yes,
the
so
weight of Ek is less than and it does the same thing. It connects the same sort of components, but the weight is less.
yeah, it need not actually connect the same components because this E prime could be going to a different component and coming back. But we don't care. So you still add Ek. You add Ek, remove this edge. Yeah.
So the cut will always have two edges?
Which cut?
Like the cut that you're doing, the circle that you're drawing, and then you're deciding that okay, I need to replace this E prime.
No, so this cut need not just have E prime. It could have multiple edges, right? Because this T could have multiple things that go out of this set edge.
In that case, if we have multiple edges,
I could have chosen a different edge also. It still
and
works.
then so if there is an edge that is going from like a third edge, and
Okay.
it is in path of that cut, but it is not connected to any other edge, any other vertex. Like
So
single.
it's just something that goes out.
Yeah.
Okay.
And if we end up picking that edge, so we will disconnect.
So you will not end up picking that edge because we are picking some edge on the path. So the tree had a path that went between the two endpoints of Ek. Okay. So let's call these endpoints X and Y. Okay. So the tree had a path that went from Y to X, and this is a path that starts at a vertex in S and ends at a vertex outside of S. Okay. So there must be some edge that crossed the boundary for the first time. There could have been multiple edges that crossed the boundary, in which case you can remove any of them. Okay. But you are looking, there has to be at least one edge because you are going from from a point in S to a point outside of S. So and path could look like this, in which case you can replace any of these crossing edges, but alright, but but these are all good questions, so you should play with more examples and then you'll realize that this is actually, I just realized this is probably the most involved argument we've seen so far. I mean, it actually has 3-4 non-trivial steps concatenated, so it's nice. Okay? So go through this again because it's nice. All right, so this is one algorithm. So this one. And I wanted to also briefly mention a second algorithm that people often consider for minimum spanning trees. It's inspired by the exact same idea. Okay, so we won't throw it in full detail, but the idea is it's actually something that someone had mentioned last class, which is that you essentially you start with a tree with one vertex. I mean, your goal is you have a full graph and you want to build a spanning tree. Right? So you want to build a tree that connects everybody. The idea behind Prim's algorithm is, let's start simple. Let's start with one node. Try to add some edge that connects, that goes out of this. Now you have these two nodes. Try to add one edge that goes out of this and so on. Okay, so that's the idea behind Prim's algorithm. So let me formally write it. So the idea is start with one node. And at each step, okay, so you have some tree, at each step, we have a subtree T, or let's call it, let's call it W. Right? So we have a subtree W. It contains a subset of the vertices. Okay. And you add one extra edge, one edge to W to increase the number of vertices covered. So let me just explain what I mean by this. Okay, so if I just have, let's say I have a graph like this. What I'll do is I will start with this W being just this single vertex. Then I'll add one edge to this. Let's say I've added this edge. Now W becomes this set of two vertices. And then I add one more edge. Okay? So maybe I've added this edge. Okay? So then W becomes this set of three nodes. Then maybe I add this one and so on. Okay? So it's just growing a tree one edge at a time. Okay? And each time I add an edge, I bring one more new vertex into the set that I'm doing. So that's the algorithm. I haven't told you how you add this one edge, right? So any guesses? How would you add an edge?
Minimum.
You add the smallest cost, yeah. So you add the edge that has the smallest cost out of the edges in W. Okay, so add the edge of min weight going out of W. Okay, so you have, initially you just have one vertex. So just look at all the edges that go out of this vertex. Look at the one that has the minimum weight. And you add this guy, let's say. Okay, so now you have this. Now you look at all the edges that go out. So maybe these are all the edges that go out. Add the one of minimum weight of these guys. Maybe it's this one. Now you have all these things that you consider. This. Okay. So you reconsider everybody whom you've not used. That's all I want. Alright, so any questions on the algorithm?
Don't we want to check if you use cycles while adding that edge, the minimum?
Alright, so that is implicit here. So I said that add the minimum weightage going out of W. Okay. So it starts at one node, it's an edge that has one node, one endpoint in W, one endpoint out.
Do we start an random node or we choose a node?
Yeah, so you start at an arbitrary node. By the way, this is, there's something to keep in mind. The word random should be used sparingly. Okay, so the difference between arbitrary and random, people tend to use them interchangeably. Random usually means there's a probability distribution and you pick it from that. So arbitrary means it's anything. So it's something to keep in mind. Right, so we start arbitrarily. So, yeah, and that's the nice thing about it. So you start with an arbitrary node, you still get to a minimum spanning tree. And so the proof of correctness actually follows the same argument. Okay, so you still say that you maintain the invariant that at every step the claim that there is an MST of G all edges chosen so far. And the proof of this is actually exactly the same as before. So can someone see why? Because the claim is very similar, right? So the claim you're saying is there exists a minimum spanning tree of G that contains all the edges chosen so far. It's just that the way we've chosen the edges is rather different now. But the proof of correctness turns out to be almost exactly identical. Okay, so let me just kind of give a hint. Okay, so now your algorithm looks very different. It always contains a W. Okay, so it has this W that it's maintaining. And I'm assuming that there is a tree T that contains all the edges that I've chosen so far. Okay, so this tree T looks as usual something like this. Okay, it contains everybody. I'm saying that suppose I look at the minimum edge out of this W. Okay, this is the edge that we are planning to add now, right? So let's say it's this edge. If it was some edge in the tree, then you are done, right? Because then there is a tree that contains even the edge that you are going to add. So just to maintain the notation, maybe I will call so assume T is an MST. Contains edges so far. And now we are considering adding EK. So there's no real K here, but just to keep the notation the same, I'm having EK. So, and now want to come up with a tree T prime that contains EK as well. So this proof is actually in some sense easier now that I think about it, right? Because so T contained all the edges chosen so far. So if this was EK, then what happens? EK was an edge that is already in T. Yeah, then there's nothing to prove, right? So it's as before. If T already contained EK, then we are done. Okay. So that means EK, the edge we are going to plan to add, looks something like this. Okay. It is some edge that we are now planning to add. And this was for some reason not in the minimum spanning tree T. Now what would be the argument?
That this would not be the case, it would already be in the tree.
And why is that?
You will be disproving this thing.
And how would that be? I mean, how do you?
But I think that should happen. I mean, EK should have been there before. It should not have existed.
Well, that's not an argument, right? It's by
We
force.
should get like the smallest weight edge every time, right?
Correct.
So, I mean, when you would have to join these two subcomponents, then you would have chosen EK already.
Well, that's still not an argument, right? I mean, in the sense that why would you have already chosen? I mean, it's not. Sure, the greedy procedure would not do it. That I agree. Okay. But the question is, why does an optimum tree? Why does there have to be an optimum tree that also contains this EK? That's what. Yeah.
There's a path out of W to the new node,
Yeah.
and there's another edge out of W that makes that path possible that's either greater than or equal to, the weight's either greater than or equal to EK.
Yeah, so this is the precise proof that we had last time, right? So what we said was, look at this tree. This tree is a spanning tree, so it connects every two vertices. Now, it did not contain the edge EK, okay? So, but it must have had a path from one endpoint of EK to the other. So again, let's call these X and Y. Let's look at the path in this. Now this path must have had some edge that leaves W. Because, I mean, remember, the path need not look so simple. It could be like this. It could be like this. But it must have had some edge that left W. Okay, it need not have an edge that goes out of X. Okay, it can look complicated. But now I will say that swap this edge with this EK. That's totally fine because we know that EK was the smallest edge going out of this set W. So, yeah, so this is always, this is the exact same argument as before. So, look at path from X to Y. Some edge crosses W, some edge in the path crosses W, and this edge is called E prime. Now again, as before, swap E prime and EK. Okay, so I won't write the details of this, but this is a fun exercise for you to just kind of reinforce the ideas of the previous proof.
So what's the difference between E prime and EK?
Sorry?
What's the difference between E prime and EK?
Oh, it's like before, right? So E prime was an edge on the path from X to Y. So T was some optimal tree. So these kind of problems actually, think of there being ties, right?
I mean, I'm just like curious to know like how was E prime, like I mean, if EK was the optimal edge, why wouldn't we able to like put it before E prime existed?
So think of two competing edges, right? So think of edge weight of EK being equal to the edge weight of E prime. This is the simplest case in which you would have to prove. See, greedy algorithms, one of the main problems is is in tie breaking. Sometimes you break ties the wrong way, and then you're off, and there's no way to complete that into an optimal solution. Okay, so think of that as being your motivation. Right? Think of trying to prove formally that can't happen. And how are we going to say this? So what we are essentially saying is that no matter how you break the ties, there's always an optimal solution that contains everything that I've picked so far. Okay? So think of it that way. Then your question is perfectly, then it's perfectly ambiguous, right? So you could either have chosen that guy or this guy. Now we are saying that there is an optimal solution that always contains that guy. Okay? Not just, So it can't happen that there's only an optimum that results from a completion of this. Okay? So there's no luck involved here, or there's no right choice. Any minimum choice is correct. So that's probably a good way to think about your question. I agree, it's a natural question, but and you would think that if this was strictly smaller than this, why would I ever pick this? Right? Think of them being equal. Then maybe there's an optimal solution only from one path. Alright, so any other? Yeah, so this one I won't dwell on it because it's good for you to kind of see this proof. It's very similar to what we've seen before. And yeah, so some of you and those of you who are noticing this probably realize this algorithm looks very much like Dijkstra, right? So you start with one vertex, okay, and you grow something, and then you add one of these things, okay, and then you add this maybe, and then you probably add something else. So every time you have something and you're growing. Okay, so you have a tree that you're growing one step at a time. So this actually looks very similar to Dijkstra, and yeah, so I think both of these algorithms appeared in the same paper even. Okay, so the first time they appeared. Okay, so this, it's just something I wanted to mention. It does indeed look like Dijkstra. Shortest path. Okay, so it's just a nice coincidence that both of them look very similar. But there you don't add the shortest edge going out, you maintain the distance from the source. Okay, and you add the shortest distance. Okay. So, alright, so the other thing I wanted to mention is how you implement Crystal. Okay, so this I won't go into, but the way we formally said this algorithm ran, we said that this is the first algorithm we were seeing, right? So we said that sort edges in increasing order of weight, consider them one by one. If an edge is unnecessary, you skip, otherwise you pick it. Right? So this is something people were asking last time, that how do I check if an edge is unnecessary? So you've got to see if, so in that example, these are the edges that I've added so far. You've got to see if the new edge is connecting two people who are already in the same component. Okay, and yeah, if so, you've got to say that, oh, they are in the same component, therefore I will skip, right? And if I do go ahead and add it, now I add this thing. Now I have to somehow update my state to say that, oh, these guys are all now in the same component. Okay, because I've connected these two, so I've made all of this into one big component. Okay. And the next time I want to check if there's an edge between, let's say, this guy and this guy, I have to say, oh, these guys are actually now in the same component. Right? So, what is a good data structure that lets us do things like this? Right? So, of course, you could always maintain the whole component in an array, and then you would get something like quadratic factor. So you can say that, oh, these are all my components of I. Each time you just go through the list of components, see if your two endpoints are the same. So it's quadratic, still polynomial. If you are happy, it's fine. But maybe you want something faster. Okay, so this is the challenge. Okay, so at each step, we need to answer the question. Are U and V in the same component? And then we should also update. Right? We need to have to update. Update. And what happens when you update? I mean, if you added an edge that went between two components. Yeah, so you get, I mean, suppose I added this edge. Now your new component is this whole thing, right? So there's some structure to the way you are actually, way these components behave, right? So every component is in some sense a set of vertices, but every time you add an edge between two components, you're basically taking a union of these two. Yeah, so what you need is a data structure. What we need is a data structure that stores sets. Okay. So again, when you talk about a data structure, you're supposed to think what does it store and what operations does it permit, right? It's just an API type thing. Okay, so you need data structure that stores sets. Okay, and given x and y, given u, v, you should be able to query if u and v are in the same set. Same set. And the other thing is you need to be able to take union of set, merge two sets. Okay, so that's union. So yeah, so this, I won't go into this, but so this is what is called a union find data structure. So it's a data structure that stores sets, it stores a collection of sets, and every time you might want to take union or you might want to find. By find I mean given an element x, which set is it in? And you can use that to answer if both of them are in the same set. If you find u, find v, if they're in the same set, then you're done. So this is what is called a union find data structure. Turns out there are some really fast algorithms for this. So it's really fast algorithm. And so let's not go into this, but there's interesting data structure. There's a nice way to maintain such sets. So there's an easy way to get a log n. There's a more complicated way where you can get something better. So yeah, let's not go there. So alright, so this is about implementing CRISPR.
Why can't you just use a hash set?
Yeah, so you can use a hash.
Hash
but how do you
sets,
merge?
multiple hash sets, and then when you merge, you just add them all, and you can add in linear time, right?
Depends on the size of the hash. But yeah,
Okay.
if your hash is big, then adding it is. Yeah, but you could use things like this. In practice, you would want to use things like this. Okay, any other questions? Alright, so the next problem I want to mention is it's a linear algebra problem. The reason I want to mention it is because it's so closely related to Dijkstra, to Pascal and so on. Okay, so the problem is the following. Okay, so it's now forget about graphs. Let's think linear algebra. Okay, so you're given a bunch of vectors. Okay, so you're given n-dimensional vectors. So this is n dimensions. Okay, so given a bunch of vectors, and so our goal is to pick a subset of this, and each vector, it's a vector firstly, so it's v1, v2 up to some vm, and each vector comes with some weight. Okay, so think of it as w1, w2 to wn. The goal is to pick a subset S of vectors such that A S spans all of Rn. So what does this mean? Is somebody else? Actually, how many of you don't know this fact? Because it's linear algebra, so many of you have different backgrounds. So I'm sure all of you have seen it, but how many of you can't recollect right away? I guess that's the issue. Yeah, because all of you would have seen it at some point, right? So the word span and stuff sounds familiar. But sorry? Oh, okay. So a set of vectors is said to span all of Rn if any vector in Rn can be written as a linear combination of these vectors. Okay, so what this means is any x in Rn can be written as x equals sum over I in S of alpha I vi. Okay. So you're only allowed to use the vectors that you picked. Okay. And so, for instance, in 2 dimensions, so I've drawn like 4 vectors here, right? So, which 2 would span all of R2? I mean, suppose I wanted to select a subset of them that span all of R2. Yeah, R2 is just the plane, right? So, what should I select?
1, 0, 0,
Sorry?
XY 1, 0, 0, 1.
Well, that's one thing, right? But I only gave you these vectors. It need not be, I mean, V1 could be something, right? V1 could be like 1, 1, V2 could be half 1, something like this. I mean, these are all, I mean, none of them could actually be 1, 0 or 0, 1.
Just 2 vectors that not equal to 0 and none of them is factor of one another.
Okay, so what he's saying is, take any 2 of these guys which is not the origin. Okay, so that's, like, I could have had a vector that's the origin. Okay, so that's a trick question. so I was not contemplating that, but let's say, yeah, so I've got to pick something that's not the origin. And in this picture, I can pick any 2 of them, right? Because no 2 of them, the only problem could happen if I had 2 vectors that kind of were parallel to one another. If I pick 2 such vectors, then I'm never going to be able to write a vector that looks like this as a combination of those 2 things. But as long as that doesn't happen, I'm able to do this. Right? So this is, yeah. So this is a standard thing. Okay, and I want to minimize the sum of weights. Okay, minimize sum over I and S W. So think of paying certain amount to get each vector, and after that I can write anybody in there, any linear combination. So I want to pay the least amount. That's the problem. So, any greedy algorithm for this? Any natural greedy algorithm? You want to add one vector at a time, right? So, yeah.
Just add the smallest weight, the vector with the smallest weight every time.
Yeah, so, let me try to do that. Yeah, so sort vectors by increasing weight. And keep adding in order, right? So, but what if the problem that he mentioned happens? So let's say I am in 2D and I have vectors that look like this. I have W1 less than W2 less than W3. Then you first pick W1, then you pick W2, then you're forced to pick W3 because you haven't spanned the whole thing. Okay. So can you in some sense get inspired by Kruskal to say that, yeah.
How long does it take to check a vector in the span of another set of vectors?
That's a good question. So it takes quadratic time. I mean, if you do it naively. Actually, I don't even know if there's a way to do it better. So it's I mean, if you have k vectors in n dimensions, then it takes n times k. Because you have to do some kind of elimination. Although if you're maintaining this, you can do better. That's different. Yeah. So any other? Yeah. So now how would you get? I mean, you can keep adding, but inspired by Kruskal, can you say if a vector is not redundant, I will add it? Yeah.
So don't add the ones which are parallel to the existing cell.
Okay, good. So that's a good point. Don't add vectors parallel to existing cell, to chosen. Is that it?
We need a stronger.
Like this works in 2D. So, but what about, yeah?
Yes, we don't want to add a vector that's a linear combination of the previous.
Okay, so yeah, so what you want to do is, for instance, if I am in 3 dimensions, okay, so now I don't want to add 3 vectors that are all in the same plane, because 2 of these guys can span this vector. So there's no point in adding this vector, doesn't give me any new power. Okay, so that's kind of the idea. Okay, so when adding, check if vector we are adding is not a linear combination of vectors chosen so far. Okay, and yeah, if it is a linear combination, then skip, otherwise just add. Yeah.
I don't know if it's related to this question, but what is the cost of checking a linear combination?
It's a good point. So anybody want to answer that? So how do you do this check? Right. So I have vectors chosen so far, and how would you check if I give you a new vector, right? So and I ask you, is this a linear combination of this and this, or something like this? So how many of you are in the ML class? The ML instructor is not going to be happy. Yeah.
Using matrices, we create a table with coefficients, and then we try to put it in diagonal form.
I mean, one way is to just say, if I can solve linear systems, I can solve this, right? Because all I want are coefficients such that thing. And hopefully all of us know how to solve linear systems, so that's one way of solving. But linear systems are a bit more tricky to solve. There's a more easier way to solve this specific problem, which is it's called Gram-Schmidt orthogonalization. So you take this vector, this is your target vector, remove all the component of this vector, and then remove all the component of this vector. Okay, so it's an iterative process that So if you don't know it, forget about it. But there's an think linear systems. Okay, so that's easy. Yeah.
So rather than sorting it, can we categorize it based on the dimensions, the vectors that are lying in